Okay, so do you all see that I'm recording there? Just give me a thumbs up if you know I'm recording. Good, perfect. You all see that it's a recording. So hopefully this is good. All right, now I'm going to share my screen. So make sure to have your PowerPoint slides open. Hopefully it doesn't all of a sudden stop on me, and it did not, thank goodness. Let me stop that. I want to make sure I'm able to see everybody as they come in too, because I have to actually have to make sure they're all good. So let me put that out there. So much setup to do. So make sure that everybody's here, and anybody who wants to be here will get into the classroom. Okay. All right, one more time, just for my sake, thumbs up if you could see the PowerPoint slide. All right, thank you all. All right, so we last left off on explaining what is delta S, right? What is entropy? And pretty much going through what type of signs, positive or negative, would delta S become, right? And we went through a couple scenarios, right? Give me a thumbs up if that was what you kind of remembered as well. Okay, delta S as it pertains to chemical reactions. All right, good. So we're gonna still talk about delta S. So we're not leaving delta S anytime soon here. We're still gonna talk about it. We're going to talk about it in the terms of the what you call standard state. So this little symbol, little dot symbol here, that tells us standard state. So we call it standard molar entropies, all right? So what does that mean? The temperature most of the time is going to be at 25 degrees C, or if you want to put that in Kelvin, it's 298 Kelvin. The pressure at standard state is going to be at 1 atmosphere. Okay, so that's what standard state means. We'll let more folks in here. All right, and I think everybody had realized this general rule, right? That entropy is greater as a gas compared to as a solid. So everybody remember that entropy increases as you are able to have more disorder move around. So that's why gas. So these are just general trends. The other general trend is the higher the mass of your molecule, the higher your entropy. So these are just general trends. So I'm going to write general because it doesn't necessarily mean for everything. So I'll take you through a little bit of what I'm trying to state here. Okay. So for example, if you went from 2 hydrogens, 2 nitrogens, to oxygen, you can see as you go down this particular row, the molar mass increases. So your delta S, or your standard state entropy, also increases. Can everybody see that trend? Yay, nay? Give me a thumbs up. You can. All right, good. So that's a general trend, but notice it stops at a certain point. Okay, so you can't compare, say, a solid and a gas in terms of molar mass. For example, okay, so water over here is 96. Okay, that weighs more than H2. Can everybody agree with that? H2O weighs more than H2. Give me a head nod. H2O has a higher molar mass than H2, right? But yet it has a smaller delta S, or a smaller entropy. So you can't compare between gases and liquids in that form and fashion, okay? So these are general trends. I just want to make sure give me a thumbs up if you understand that when you're comparing these, make sure you're comparing it all from gases, all from liquids, all from solids, and so on and so forth, because it's a general trend. Good. All right, we're gonna move on now. Oh, getting a lot of emails, actually. Gotcha, I see. All right, so let's do a couple of calculations. You've seen this before. We're gonna calculate we're going to calculate delta S of the reaction. Okay, how do we do that? We calculate pretty much by taking the product minus the reactant. So we're going to do product minus the reactant. Raise your hand if you've seen this before. We did this with delta H, right? We're doing this again now with delta S. So I'm going to give you a table, an entropy. So you're going to use the standard molar entropy table, kind of the one I told you right here. So this is the table. This is the table, okay? So we're going to use that table to pretty much solve for delta S of the reaction down below. Holly, go ahead.
Oh, no, you said raise your hand. Sorry, I didn't mean to.
Oh, gotcha. All right. You're good. You're good. All right. No worries. No worries. All right. So once again, right, we're going to calculate. This is what we're doing in this slide. So we're going to calculate this. And how we're going to do that? We're going to get products minus reactant in terms of the table of entropies that we just saw. So from the table, hydrogen gas was 130.6 kilojoules per mole. Kilojoules per mole, and actually per Kelvin, if you want to get technical. All right, nitrogen was 191.5, and ammonia was 192.5. So all of this is in actually in joules. So these units are in joules per moles Kelvin. All right. So once again, 130.6, 191.5, 192.5. Once again, these were all given to us in the entropy table. All right. So we're going to times this by 3. Why? Because there's a 3 in front. That's the coefficient for this reaction. We're going to times this by 1 because there's just nothing in front of that. We're going to times this by 2 because there's a 2 in front of that. Everybody good so far? All right. And we know that, let me adjust my iPad here. And we know that this is our product. And these two are our reactants. Okay. So our delta S of the reaction here is going to be product minus reactants. All right, it's going to be 192.5 times 2 minus 130.6 times 3 plus 191.5 times 1. So what you should get here should be negative 198.3, okay? And once again, this is in joules per mole degree Kelvin, in kelvins. All right. Everybody see that? So we're calculating delta S using the entropies in the table. These are all in standard state. All right. Any questions? No questions? Let it, all right. Rob is giving me the thumbs up saying I should move on once everybody has written it down. Of course, this is recorded as well, so you can always come back and watch if you would like. Okay. So I'm going to move slowly. I know someone's going to tell me to go back, but no one's saying anything, so I'm going to keep going. All right. So we're moving on to, we're still sticking with delta S. We're still sticking around with entropy. We're going to talk a little bit about what the second law of thermodynamics, okay? So the second law of thermodynamics states that a process or a reaction is spontaneous if the entropy of the universe increases. So spontaneous if the entropy of the universe increases. all right? So any spontaneous process is, so I'm just kind of repeating this, any spontaneous process is an increase in entropy of the universe. So there is a theory out there that the universe is ever so expanding. Okay, raise your hand if you heard that part, that theory. The universe is always expanding. I get a clap. I got a clap. Perfect. So this comes from the idea of this is a spontaneous process. We're all eventually going to contribute to the universe as it expands, as we degrade into different, smaller molecules, as the universe, so, as more and more of the, I guess, potential solids might flow into as a gas out and expands, right? Any spontaneous process is increasing the entropy of the universe. All right, so we talked a little bit about systems and surrounding, right? We talked about this is the system, then this is the surrounding, anything outside of it. If this was a system, anything outside of it is the surrounding. We talked about that. We could talk about it in terms of the delta S or the entropy as well. So the system plus the surrounding, pretty much everything will be considered the universe. And I also realize how bad I am in writing on an iPad. All right, everybody good? System surrounding everything. When you include them all the entropies, we got the entropy of the universe, okay? When I write the delta S of the reaction, I am actually telling you that it is the delta S of the system. So hopefully no one's been confused when I write delta S reaction. That really literally means the delta S of the system. All right, thumbs up if that makes sense. Every time I wrote a reaction, that really means the system. So we all are in the same vocabulary, have the same vocabulary, have the same understanding and terminology, okay? All right. So I'm gonna describe the universe for now. All right, I'm gonna describe in terms of delta S. So if delta S of the universe is positive, then the process is spontaneous. Always ever expanding, expanding, expanding. If the delta S of the universe is negative, then this is a non-spontaneous. It's non-spontaneous process in a given direction. All right. Note that the delta S of the universe is the sum of the delta S of the system and the delta S of its surrounding. So if you just were like, Dr. Z, you're just going in circles. I am going in circles for a reason, because it will get lost very easily for you all if we don't define what is the system, what is the surrounding, and what is literally everything, okay? Everybody good? Shall we proceed on to the next page? All right, good, good. Okay. So there is a connection. I talked about how everything we talked about so far from last chapter and this chapter is called thermodynamic, right? Last chapter was delta H. This chapter is delta S, but they are related. They are related, okay? So the heat that is transferred, all right, the heat that is transferred between a system and a surrounding results in a change of the entropy to the surrounding, otherwise known as, just looking at this equation, can everybody see that? Delta S of the surrounding is equal to how much heat the system is giving off. So that's why we got delta H of the system there, divided by temperature, okay? So notice this is your delta S of the surrounding is equal to the amount of heat, right? Delta H means heat of the system is given off, right? Remember, this is our system, and literally it's giving off heat to our surrounding. We'll call this surrounding, all right? And it's going to change. the entropy of our surrounding delta S. So the delta H here is going to change the delta H of our or the delta S of our surrounding. Got it. Thumbs up, thumbs down. These are the relationship between delta H and delta S so far as we know. Okay, good. All right. So if delta H of the reaction is negative, let's do a little, we got to make sure we can define some of these symbols and signs. If delta H of the reaction is negative, then heat is transferred from the system to surrounding. Okay. I feel like that person from South Park. I don't know if anybody knows what I'm talking about, but is that teacher? He always goes, okay. That's exactly what I feel like right now. And I can't get anybody's reaction on the other end because no one, except for Ivan. So I appreciate you, Ivan. Delta S of the surrounding is then positive. Okay. If our delta H of the reaction is positive instead of negative, right? If it's positive, then we're saying that heat is transferred from the surrounding to the system. And there in turn, our delta S of our surrounding or entropy is going to be negative. All right. So flipping in opposite signs, make sure you know what we're talking about in terms of the system and the surrounding, right? We're talking about delta H of the system. We're talking about delta S of the surrounding and how they're related to one another. All right. We're going at a pretty good pace. Slow me down, ask some questions, write it in the chat box. Oh, I got something in the chat box. Oh, Mr. Mackey. Yeah, they're right, Teresa. That's exactly who I'm starting to sound like, by the way. By the way, I did get a second interview for my Pasadena City College job. And that was today in the morning that I had my second interview. And I don't know if they're going to call me back. So I think this is probably where I'm going to end my interview stage there. So I won't be Mr. Mackey quite just yet. Won't be a full-time instructor yet. But the grind continues on for everybody, for you all and for me as well, right? We're in the same boat, like I said. We're all just reaching for our dreams. All right. So with that in mind, let's go and practice some delta S of the pretty much universe. All right, so let's do a little practice here. Consider the combustion of propane. So we talked about delta H of the reaction. If this is negative, can you all just write on the chat, tell me real quick, if this delta H is negative, is that an exothermic reaction or endothermic? Just wanted to test if you all remembered a little bit, exo or endo. Is it releasing heat, exo, or is it taking in heat, endo? EXO or ENGO? All right, so I got a couple of you to participate there, and I appreciate that very much. So this is an exothermic reaction. All right, perfect. Okay, so we got an exothermic reaction. Can we predict the reaction for entropy here? Can you predict if this is going to be either positive or negative? Can we predict that based off of just the amount of moles of gas? Meaning the amount of moles of gas on our reactant side, the amount of moles of gas on our product side. We had this, I think this is just last week where we said how much moles of gas on either side will make us predict the delta S being positive or negative. So we have 1 plus 5, so we got 6 moles of gas on the left side. 3 plus 4, that's 7 moles of gas on the right side. So from just looking at that, let's get some volunteers from different folks who haven't yet put in the chat if you think delta S of the reaction here is going to be either positive or negative based off of just that moles of gas. So some other folks to tell me just write plus or negative on the chat, or positive and negative. You can write the word out as well. Let's get some brave volunteers in there. All right. Awesome. And thank you. Thank you for that. It is positive. Perfect. Based off of just the moles going from 6 to 7. We're expanding, having more molecules, increasing the microstates, as you know, we talked about before. All right, good. And then remember, we had this equation from the last, all right? We had this equation from the, just up here. Can everybody, or just from here, this is where we got this equation. All right, so the system, like I said, the system here is the same as reaction. So we got there, so these two are the same. So if our equation here where delta H is negative, what do you think is going to be our delta S symbol? Would it be delta S of surrounding positive or negative, right? We made this prediction up here, right? If delta H is negative, delta S is positive. I'm sorry, I just went right for it and just wanted to tell you the answer. But everybody see where that's coming from? Okay. All right. And then let's put this all together. So we got delta S, oops, excuse me. Delta S of the universe is equal to delta S of the system plus the delta S of the surrounding. And we got positive here, we got positive here. So this must then be positive. So what does the sign of the delta verse of the universe tells us about this reaction? It tells us that the reaction is spontaneous. So far, so good. Thumbs up. I mean, we've covered 4 slides in 20 minutes, roughly. We're going at a pretty steady pace here. So please stop me, or even, you know, ask me a question, direct chat. If you don't want to ask it in front of everybody, it's all good. Because we're going at a pretty good pace. All right, so another way to bring this all about is, instead of talking about the spontaneity, if it's spontaneous reaction or non-spontaneous reaction, instead of using the delta S of the universe, we could use something called delta G. Delta G is referred to Gibbs free energy, okay? So we can now use delta G instead of delta S of the universe to describe if something is spontaneous or not, okay? And how does delta G relate to delta S of the universe? It relates by this equation down below. Actually, it's better if I do a highlight. So it relates through this equation. Delta G is equal to our delta H minus T delta S. And once again, this is, and sometimes it's not written there, but this is of the system, all right? Of the system. And remember, system can also just be, you might see it as just reaction, but they both mean the same thing. Because the reaction, chemical reaction in our case, is the system. Okay, thumbs up if this makes sense, right? We're now going to substitute in delta S of the universe with this thing called delta G. And delta G is going to be our big player in terms of what is spontaneous and what isn't spontaneous. All right. Okay. So if delta G is negative, this reaction is considered to be, oops. So we got to do some definition. Is going to consider to be spontaneous. So notice if it's negative, notice it's negative now. it's spontaneous at the given temperature. If delta G is positive, this is not spontaneous. So we're switching the symbols a little bit, roughly because of how this equation is formed, okay? Everybody see the big distinction that's going on? So if delta G is negative, this thing is spontaneous. Very different from when we talked about the delta S of the universe, okay? The signs here flip, and it really does matter a lot, okay? And it has, once again, to do with this equation. But they talk about the same thing. They mean the same thing in terms of referring to what we call spontaneity, if it just, reaction would just go without any much of a push, or if it needs a push to go. Thumbs up, thumbs down. I'm gonna let that sink in a little bit. We wrote a lot. I definitely would like some questions if you have them. Yeah, no questions, huh? If you want to just direct message me, this is the perfect time, and I won't call your name out. So no, I won't be calling you out. All right, everybody looks okay. So nature, pretty much anything around us is considered nature. It says nature favors processes that are exothermic. So delta H normally is negative. So exothermic. And where the entropy happens to be always ever expanding. So delta S, always expanding. So you can call it increasing. Okay, so those type of processes we know will always be favored most of the time. So really, this is the part where I really want you to kind of think about it, understand what it means to transfer heat. What does it mean to change phases? How does it overall contribute to some molecule that will either react with another molecule spontaneously versus one that needs a little push, needs a little bit of energy and input, okay? Sounds good, perfect. All right. So let's do a little bit of practice, okay? So there are 4 cases here, okay? There's case 1, case 2, case 3, and case 4. And we're going to relate everything that we just learned. We're going to try to relate as best we can delta H, delta S of the surrounding, delta S of the universe, and then now delta G, right? We're gonna do all of that in one paper in 4 different cases. All right, are you all ready? I'm gonna do one for you, and then I'm gonna put you in breakout rooms, and I want you to do the rest. Does that sound good? Give me a thumbs up if this makes sense. I'm gonna do one for you all, and then we're gonna break out into rooms so that you can do the rest with your friends. All right. So for example, if delta H is negative, so if this is an exothermic reaction, and once again, I'm just gonna put system in here so everybody knows that those are the system, right? So that's exo, and this right here is positive. So we're saying that this is increasing. Okay. All right, all good. And remember, delta S of the surrounding is equal to negative delta H of the system divided by T. And so our delta H up here is negative. So that means our surrounding has to be positive. So I'll even circle it. Can everybody see that so far? Yeah. Right. And so our delta S of the universe is equal to delta S of the system plus delta S of the surrounding. All right, let me go zoom in on this so I could probably write it better. Surrounding. And we know that this is positive, this is positive. Therefore, delta S of the universe must be then positive. Everybody get so far? Thumbs up, thumbs down. I'm trying to make sure that everybody gets these equations. Some of you are probably still writing. That's okay. Thank you, Navy, for giving me that thumbs up. All right. All right, and this, once again, these are of the system. Okay. So if we look up here, our delta H of the system is negative. Our delta S of the system is positive. So if we have a negative number of delta H minus a positive number over here, delta G should be overall negative. Can everybody see that? All right. I'm stating that if this is negative and it's minusing a positive number, your delta G should be negative. All right, doing some very simple mathematics there. All right, everybody. So what does that tell us? That tells us that delta G, in this case, is going to be negative at all temperatures. Okay, so that means right here, let me write that a little bit better. So that T there, that's temperature. So no matter how much you increase or decrease that temperature, these signs will always be the same. Delta G will always then happen to be the same. Everybody, should I repeat that? No one is asking for a repeat. Okay, okay. All right. Are you all ready to go into your breakout rooms to do cases 2, 3, and 4? If you need to take a screenshot, please take a screenshot of it now. All right, when you're taking a screenshot and you're ready to go to breakout room, give me a thumbs up. All right, good. So let's do that. We're gonna go breakout room. How many breakout rooms? Let's go. We got 20. Let's go 5.
Dr. Z, I have a question.
Go ahead. Perfect.
At the delta S surrounding,
Uh-huh.
is that always gonna be positive? Because I was starting to do the next one, but this I'm looking at the slides from 2 slides back,
Yep.
and it says if the delta S is positive, so is the delta H system divided by the T, is that just gonna be the same? It would be still negative?
You're this one, you're talking about this one right here, right?
Yeah.
Yeah, so if we do this, once again, like that, right? Because that's the equation that they're related to each other, right? If the delta H here is positive, that negative is still on the outside, making this,
Positive.
making that negative. For example, if the delta H here was negative, and let's put this as negative, you got negative multiplied by a negative, that should then give you a positive. Should I repeat that, Teresa?
Yeah, do it one more time.
Okay, I'll do it one more time. Perfect. I'll do it one more time. All right, so this is the equation, right? This is the equation that relates delta S of the surrounding and our delta H of the system, right? If we say our delta H here is positive, it's going to be positive times a negative, would give us a
Negative.
negative. So this would be negative. However, if we said that our delta H is negative, negative multiplied by a negative will get us a
Positive.
positive. See how I did that?
Oh, got it. Okay. Okay,
Perfect.
thank you.
That is a great question. I'm glad you asked that because I'm pretty sure everybody else is benefiting from your question. All right, ready to go? Anybody else got a good question like Teresa did? Because that was a great one. Anybody else has a clarifying question that you'd like to know? All right, I'm gonna give you 5 minutes. I'm gonna maybe go in, maybe 5 to 7 minutes, okay? So go for it. I'll join in, talk to a couple of y'all. Okay, Rob, Rita, Mariana, don't want to go into these? All right. Hello, Daisy. Oh, hey, Sarah. Mariana,
Hi.
how are you all doing?
Good. How are you?
Doing good. Aren't you all happy to be at home and cozy on a cold night?
Hello.
A little. Okay, I'll take that as a yes. um, any questions for me about this delta S, delta G shenanigans here? No. Can I come back to you all?
Mm-hmm.
All right, I will do that.
Anything.
Hi, Dr. Z.
All right. I heard Kyle's voice. Are you doing okay, Kyle?
Yeah, I don't feel good. I'm on the struggle bus.
Yes, all right. All good.
Mm.
All good. You stay bundled up and grab a lot of emergency and a lot of water.
I've had pho twice in the last 2 days,
Oh
and
my God, I had pho on Saturday.
I don't eat soup.
Oh,
Like
God.
I don't like soup, and I don't like soup or noodles, and I just like cannot get enough of it. I'm just like,
Delicious anyway. So.
I'm glad. I'm
Anyway.
glad. I'm gonna guess that you all are doing okay with this. And I just wanted to check up and just see if that was
It seems pretty easy because it's literally just like algebra.
okay.
yeah.
Okay.
Negative, negative, positive.
I agree. It is just very much perfect. But no questions for me so far.
No.
Not yet, no.
Cool.
No.
All right, then I will go and help another group.
Darium. Oh, hi. Hello. I don't know what was going on with my phone, that it wasn't letting me connect. And then I tried connecting with my computer and the same thing happened. So I don't know if it's my Wi-Fi
Yeah.
or what it is. But I ended up coming to Starbucks because
Let's see. No worries, you're good.
And
Brittany. You're good.
it's really loud in here.
No, you're right. That's nothing new to me. That's nothing new to me. Are you all good? Give me a thumbs up if you all are able to do this. Otherwise, if you have questions, please let me know.
Can you check if I'm doing mine right? I'm gonna share my video. It's on my laptop, so it might be hard to see.
How about you just tell me positive, negative symbols?
So for case 2, for obviously the first one's positive, the second one's negative. The surrounding, it's negative,
Yep.
And then the S universe is negative because
Yep.
since the system is negative and the surroundings negative, that makes it negative.
Perfect.
And then the delta H is positive, but
Mhm.
see, that's where I got confused because it's minus.
Yep. Mhm.
So if it's up plus minus a minus, that equals minus, right?
If it's a plus that minus a minus, it's going to be always a positive.
Oh, it's a positive.
Yeah,
Oh.
it's a weird algebraic rule, but yeah, that's how it goes. Those two minuses kind of pretty much cancels each other out.
Oh, okay, that makes sense.
Yeah.
The other way around, it would be negative.
You mean if you had the negative in the delta H and the positive
Yeah.
in the delta? Yes, exactly.
Okay, and then for case 3, it's negative, negative, positive, negative, and then the last one is negative.
The delta S of the universe can either be positive or negative, depending on certain cases, pretty much depending on the how big or large the surrounding is versus the system. So we'll talk about those cases. Those cases, the case 4 and 3 and 4 are very unique.
Oh, okay.
Those are the ones that you most likely encounter on your exams. So,
Oh, okay. I'm gonna highlight them then.
because they're the ones that are most unique to ask questions about.
Oh,
Can
okay.
you repeat that again? What questions were they?
You're talking about questions. Michelle was asking about cases 3 and 4 and why delta S of the universe might actually be positive or negative. And we'll talk about that when we get back into the main class, Brittany.
Okay, thank you. Also, I think somebody else was trying to join, but they weren't able to join, so we came out off of it.
It's all
Our
good.
group.
I'm gonna close the rooms. Okay, I'll see you guys back into the main one.
Okay,
Okay,
thank you.
Let me mute myself.
All right, everybody, welcome back. Hopefully you had some time to talk it over with your neighbors. I know it was a very short conversation. All right, let's see if we could get everybody back. I think we're gonna get everybody back here soon. Okay. All right. Everybody good? No, we're getting back. We're getting everybody back. Slowly but surely. I think I'm hearing Kyle's whistling.
Sorry, it's the kids outside.
It's okay. You're good.
Shut up, kids. I got it.
Yeah, sure. All right, everybody good? Okay, so let's finish case 2 here. So case 2, we got delta H is positive, delta S. So once again, these are systems, right? I didn't write that in, or the other professors didn't write that in, but these are delta H of the system. Delta S of the surrounding here is negative. Delta S of the universe here is negative. So once again, these are of the systems. So let's fill this in. So this is positive and this is negative. Therefore, delta G here should be positive. So delta G is positive for all temperatures. What does that mean? That means if this temperature here, doesn't matter if it's cold or hot, this delta G of this whole entire system, right? This means system, by the way, is always going to need an energy input. So this is what we call non-spontaneous. Spontaneous. This is what we call spontaneous, okay? Gosh. Everybody good? So those are the easy, I would say, cases. Cases 2 and 3 are probably the easiest cases. Maybe I should put it in green because those are supposed to be our easy cases, okay? Cases 3 and 4 are what you will likely see more of on your exams, quizzes, because they're a little more difficult ones to assess, all right? So let's look at these. So if delta H is negative, and this is of the system, once again, delta S of the system is negative. Here, all right, delta S of the surrounding should be positive. Delta S of the universe, which is equal to delta S of the system plus delta S of the surrounding. So make it bigger. So we have positive here and we have negative here. Can you make a guess if delta universe is positive or negative just based off looking at these symbols, right? Just looking at these symbols. Can we even make a guess if this delta S of the universe is negative or positive?
Negative.
So one person is saying negative. Is anybody else thinking positive? Or is someone thinking maybe you can't tell? All right, and you cannot tell. You can only tell depending on if this number, right, depends on the magnitude of delta S of the system or delta S of the surrounding. Does that make sense? So if you have a bigger number here versus a smaller number on this side, then you're gonna have a negative number. If you have a bigger number on the right side, that's positive, but a smaller number on the left side, then overall the delta S of the universe will be positive, okay? So it depends on the magnitude. Okay.
Can you say that one more time, Dr. Z?
Oh yeah, sure. It depends on the magnitude of the number of these numbers. So for example, if you had negative 15 plus, say this one is smaller. So this is a smaller number and this is a larger number, all right? Is the overall number gonna be negative or positive? This
It
would
would be negative because of the larger number.
Exactly. So now let's switch this. What if this was a smaller, magnitude-wise smaller number, and this was the bigger number, right? I'm sorry, this is supposed to be positive. This is supposed to be negative. There you go.
It'd be positive.
It would be positive. So it depends on the magnitude of the numbers, right? The delta S of the system, delta S of the surrounding, depends on how big or small those numbers are. So that means our delta S of the universe, can either be positive or negative, okay? It could be either one, depending on the magnitude. Everybody good with that? It's not a satisfying answer, but it's one that you will most likely encounter on your exam because I can put actual numbers to these systems and then you have to then calculate. So these will be the more, I would say, challenging questions to put on an exam. All right, so let's go back down to this one, okay? So if this is H of the system is negative, if this delta S of the system is negative, what will be our delta G? Any guess? No guess?
Positive.
So we got some good, so it can be positive. So delta G here could be positive, or it could be negative. It could be either one, actually. And it all depends on the temperature. It all depends on the temperature. Okay. So if delta G is going to say be positive, this is going to happen if the temperature is high, a high temperature. Because overall, if temperature here is very high, you got say like 20 or 200, maybe even 300K times this, this overall number is going to be very, very, very much large. So if you have a negative number multiplied by a very large negative number already, this is going to be overall positive. So a lot of small little algebra questions here. Reverse side of that, if our delta G is going to end up being negative, that means this delta, the temperature is going to actually be at a low temperature. So this is going to be cold. This is going to be hot. Okay. Thumbs up, thumbs down, right? So this depends. This depends on the temperature. If your reaction is at operating at very high temperature, and these systems right now, the delta G will be positive. If your system, your reaction is operating at a low cold temperature, then the delta G might be, will likely be negative. Okay, for this.
Dr. Z, I have a question.
Go ahead, Michelle.
Why is the where the minus T delta S negative?
Why is it negative?
Yeah.
So this, oh, sorry, go back. So why, right here, why is this negative?
Yeah.
Where does that come from? It comes from over here.
Oh, okay.
Making sure I didn't lose anybody. Did I lose anybody? Maybe I should give you a different color. So this color combines there. This color goes here. Everybody see that? And if you are colorblind, I am so sorry. If you are a person of color blindness, that is my fault. So please let me know later on. All right, everybody good? It might take a while to sink in, and that's totally okay. All right, so we got the last case, delta H's of the system is positive. Delta S of the system is positive. Therefore, our delta S of the surrounding, if we look at just the delta H, right, this is going to be negative. Delta S of the universe can be either positive or negative. And lastly, if that's the case, plus and plus, delta G will be positive if you have a system at high temperature. Delta G here is negative if it's at a low temperature. Once again, just to remind everybody where I am getting these numbers from. All right, I'm getting it from here and here. Notice they are flipped. Cases 3 and 4 are pretty much the reverse of each other. I'll wait for you all to write. And then hopefully someone has a question for me. If not, it's okay because we have another page literally summarizing this in case the equations don't quite make sense. We're going to put it into words as well, into, you know, a string, an actual sentence that you could read, and hopefully then you have the mathematical relationship and some ways to just kind of read and kind of assess it and read it out loud to yourself, and maybe it might, you know, make it be clear for you all. Can I move from this slide to the next? All right. If no one else is telling me no, I'm going to move. All right. So once again, here are the different cases that we saw. Case 1, case 2, case 3, and case 4, right, everybody? So this is once again delta H of the system, delta S of the system, right? And we talked about, will this be a spontaneous reaction? And remember, spontaneous reaction, we're talking about delta G, all right? Or you could put system if you want there with delta G. So it's spontaneous when the delta H is negative, delta S is positive. This is spontaneous at all temperature. At any temperature, this is going to be good. For case number 2, okay, where the delta H of the system is positive, delta S of the system is negative, this will always be non-spontaneous at all temperatures. So case 1 and 2 are reverse of each other. Case 3 and 4 are also reverse of one another, where this is spontaneous only at low temperature, while case 4 is only spontaneous at high temperature. So these are all mathematically fixed ideas, relationship to one another. How does heat relate to spontaneity? How does entropy, increase in chaos and order, and microstates relate to spontaneity, right? But really all we're talking about is how a reaction just reacts without any energy input, or does it need energy input? And how do we know that? We are literally judging it based only on these 2 criteria, delta H and delta S. Those 2 lends itself to tell us if this is spontaneous or not. And delta G is the sign of delta G will tell us if it's spontaneous or not. Okay. I know I'm just repeating back and forth, but eventually I think it will definitely, it'll take you a lot of practice problems. And if you're unsure, of course, you could always ask. And there is a lot of textbooks out there that you don't need to buy that talks about pretty much spontaneity. Everybody good? Can I proceed to the next slide? Yay, yeah. All right, I'm going. All right, so here we go. So we're going to talk about this process here. This is water in a solid state, right? Pretty much ice. This is water in its liquid state, water, okay? So we can look up once again the delta H, right? This is standard state. Remember that little, I'm not doing a good job here. Let me zoom in. Remember this little 0 dot above, that means it's at standard state. Okay, so we can look this up in a textbook or a table and it'll give us this number. Same thing over here. We see that it's in standard state. So we can look this number up in a table. Okay. All right, so those numbers are given for this process right here, for this process, which is called melting. So we are literally melting ice. Okay, we're melting ice. And we want to know, is this process of melting ice going to be spontaneous or non-spontaneous at 25 degrees C? What's your guess? Do you think you would melt ice at 25 degrees C? Yes or no? Go ahead and just type it in the chat. Yes or no, do you think you will melt ice at 25 degrees C? And by the way, what is room temperature? Like, what are we feeling right now in our room? Except for maybe a couple of you who might be sick. You might have your temperature in your room raised up a little higher, but yep, so the question is, do you think ice will melt at 25 degrees C? So room temperature, by the way, room temp is anywhere between 20 and 23 degrees C. That's room temp. So will ice melt at 25 degrees C? Yes or no? I'm hoping to get some more folks in here. I think I only got 6, so let's get out there. Okay, so I'm seeing more yeses now than nos. And it's okay to say if it goes slowly, it's totally fast. We're not talking about how fast it goes. We're just saying, will it go? And will it be spontaneous? Meaning, do you need to put a hair dryer and blast the hair dryer on it to go, right? That's inputting energy. Or you just leave it and it's gonna just go on its own and it's gonna melt on its own. All right, So let's do the math. Let's actually do the math to check this out. I know you probably all know the answer already because you can actually do this conceptually and experimentally, but let's actually do the math to actually figure this out. Okay, so we got this equation that we could use. Okay, all right. This part of the equation is here. We'll plug it in. This part of the equation is here. Can everybody see that? Just want to make sure everybody's good. So let's make sure we plug these all in. So we got delta G is equal to 6.03 kilojoules per mole. Okay, minus T 0.0221 kilojoules per mole Kelvin. So why is it this number? Why isn't it not 21? Or why is it not 22.1? Because we actually have to convert joules to kilojoules first. Can everybody see that? So that this kilojoules and this kilojoules would match. Everybody, can you all see why I put 0.0221? Can you all raise your hands? All right, I got Navy to raise their hand. Can you all, other people, raise their hand? Otherwise, if you don't raise your hand, I know someone's going to ask this question. Where did this number come from, right? Convert joules to kilojoules, all right? All right, and what is our temperature? And our temperature better be in Kelvin because we got Kelvin over here. So we got to convert 25 degrees C to Kelvin, and that literally is, you know, the equation. If you all want to write, remember is that plus 298 equals Kelvin, or sorry, 272. Oh boy, 272. 273. So that means 273 plus 25 is 298. So let's put that in. 298 Kelvin. Can everybody hopefully see that? Okay, so let's plug this in. Equal negative 0.55. So I got 5.6 actually kilojoules per mole. So notice it's negative. So this is going to be a spontaneous reaction, okay, at 25 degrees C. All right. Awesome, perfect. Good, so everybody see where the numbers are coming from. Once again, this is from the green. This is from the red, okay. Good, 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 good. So negative means, negative delta G means spontaneous. Positive delta G means we need to put some energy in there, okay. All right. So it's not a big number, right? We got 0.56. It's not a big number. So most of you are saying it's going to go slow, but it's going to go, right? It's going to go, but it's going to go slow. So that magnitude, that number, that small number is telling us that it's probably not going to, you know, it's going to go for sure, but it's maybe not, it might not go as quickly potentially because it doesn't have a pretty high delta G. But remember, we're talking about thermodynamics here. We're not actually talking about kinetics. Remember those good old kinetic days, right? Kinetics is all about speed. Thermodynamic is about heat and pretty much everything that isn't pretty much kinetics. All right, so the biggest thing we're really worried about is the sign. All right. Everybody, thumbs up, thumbs down. Everybody good? Are y'all good? Y'all feeling okay? Perfect. All right, now I want you to practice on your own here. I'm going to ask the same question. Can you calculate delta G? Can you calculate delta G? But this time, instead of at room temperature, I want it to be at cold temperature, negative 25 degrees C. Do you think delta G is going to be positive or negative? Do you think this is going to be spontaneous or non-spontaneous at negative 25 degrees C? Remember, ice freezes at 0 degrees C. So freezing happens at. So what do you think is going to happen? Is it going to be, oh, Navy? You had a question? If you do, go ahead and ask. Oh, okay. The hand function is just being all good. All good. All right. So I want you to do the same thing, but down here, right? I want you to calculate delta G. Okay. You should remember the delta H and the delta S at standard state should still be the same. The only thing that's different now is what happens when this process is at negative 25 degrees C, not positive 25 degrees C. What do you think is going to happen to delta G? Is it going to be positive? Is it going to be negative? Can you do the actual numbers to actually tell me what number you're going to get as well? Okay. And I want you to just do that on your own. Take about 5 minutes. And I want you to write the number on the chat. And I want you to direct message me. So not just put it in the chat for everybody to see. I want you to tell me the actual number by direct messaging me on the chat. All right. Okay, I see.
Dr. Z,
Uh-huh.
do you have to convert to kilojoules, or because I converted to joules, does it matter?
You can convert the delta H to joules if you want, and then keep the delta S as joules, or convert the, you know what I mean, or convert the, like we did in the first part. So as long as you keep the joules consistent or kilojoules consistent, I'm totally fine.
Will you specify what you want?
Oh yeah, I normally do, right? I normally tell you all like liters or grams, so I try not to leave that up to interpretation.
Okay, thank you.
All right, okay, it's looking pretty good. Interesting, good, good, good. I'm seeing a lot of non-spontaneous, and that's a good sign. All right, as you're doing that, let me write this in. So it's still the same, 0.03 kilojoules per mole minus, so I'm gonna put T here for a second, 0.0221 kilojoules per mole Kelvin, okay? So the T here is from that. So we got negative 25 degrees C plus 273, and that should get us to 248 Kelvin. Okay, everybody? So that means this number here should be 248 Kelvin. And I believe this should get me to 5 kilojoules per mole. So not 5.6, but 5.5. All right. Does that check off everybody? Oops. I'll do a little color coding here for everybody. Good so far? Any questions? So once again, note that this is, so this is positive delta G. So this is non-spontaneous. That's negative 25 degrees C. And it makes sense, right? You would not expect ice. So pretty much it's saying you would not expect this reaction. You would not expect this reaction to go at negative 25 degrees C. You wouldn't expect ice to melt at negative 25 degrees C. Makes sense, right? So that's why it's non-spontaneous. It won't go unless you give it some heat, you know? Everybody good? Makes sense? This is the start of more delta G's. Let's start a good old Gibbs free energy. All right, let's talk about pretty much how can we tell at what temperature the delta G sign will flip. When will delta G go from positive to negative? When will delta G go from negative to positive? All right, at what temperature? So in order for us to understand or figure out what temperature that may be, we need to set delta G to 0. Everybody, you have to set delta G to 0. So if we set delta G to 0, so over here, if we set it to 0, we could then reflip this sign to solve for temperature. Okay, just like so. So we're setting delta G to 0. And then what I'm going to do now is I'm going to move this over to the left side. Okay. So what does that do? It's going to be, so I'm going to add, so pretty much I'm going to do delta S on this side plus T delta S on this side. And what it's going to look like is now delta ST equals delta H. All right, I didn't lose anybody, did I? No, everybody good? All right, from now on, I'm going to divide by delta S on both sides. So last thing I'm gonna get is delta H divided by delta S. This is what I want. Okay. I found this to be somewhat confusing, so I'm just gonna take off that. All right, so this is what I want. So rearrange equation to find T. All right, now we could go back and look by using this equation. All right, and figure out exactly at what temperature is delta G going to be negative, at what temperature delta G is going to be positive. So we'll take the numbers that we got from the top. So for this case, once again, for melting ice, we had 6.03 kilojoules, right, per mole. And we had 0.0221 kilojoules per mole in Kelvin. And this should come out to be 272.85 Kelvin, or if you want to just, it's close to 273 Kelvin. So we just call that the answer here. So if the temperature for this system, for melting ice, if this temperature is above 273 Kelvin, delta G is going to be negative. So that's spontaneous. All right, so if it's above room temperature, if it's above, so this is actually at 0 degrees C. So if it's above freezing, 273 is above freezing, you're good. If the temperature is equal to 273 Kelvin, delta G is equal to 0, no change. If delta T is smaller, or if temperature is smaller than 273 Kelvin, then delta G is going to be positive, non-spontaneous. All right. That's a lot. We're really, I mean, you're taking this with stride, so that's great. I don't see that many questions though. Do we have any questions so far? No? Okay. All right, this is the last slide because we're approaching the end of class. Okay. So we could do a bit of practice here, okay? So once again, we know that delta G is equal to delta H minus T delta S. We have delta H here. We have delta S here. All right. We got temperature here and here. Everybody see that? So we're trying to figure out this process, the bromine 2 of gas going to bromine 2 of liquid. What can you calculate the delta G at 25 degrees C? And then can you calculate the delta G at 45 degrees C? Or, you know, can you calculate both of them? So this would be delta G, and this other one would be delta G. So this one will be at 25 degrees C, and this one is at 45 degrees C. Give me a thumbs up if you think you could tackle that part based off of what we did from the top. Okay. Make sure to do the conversion, right? So this is J here, it needs to be converted to kilojoules. These need to be converted to Kelvin. All right. Yeah, TOs has to be Kelvin. The reason why TOs have to be Kelvin is because we have the K here. And the K here needs to be canceled in order to just have kilojoules per mole as delta G. So unless we're able to find this in terms of degrees C, then you could just not have to do that conversion. But because it's in Kelvin, we have to do the conversion to cancel out units. Okay. All right. Can I entrust you all to do this at home as a homework? And then we'll meet each other up on Wednesday to then talk about this particular one. So this would be your homework problem for the day. Thank you, Navy. Thank you for giving me a thumbs up. Another person giving me a thumbs up as well. All right. So it's 6:50 and right at the end of the class. So this would be homework. So I want you to take this. You're already home. You might as well go ahead and try this out at home. Right. And there is lab. There's a virtual lab. The lab, you have to watch a bunch of YouTube videos, and then you have to then answer the question. All right, everybody, y'all hear me? You have to watch a bunch of YouTube videos that's already on the paper that's given to you, and you have to answer the question. The one thing I will say, and I'm going to skip down here real quick, and I want you to take a screenshot of this if you can, is that for one of the questions, they're going to ask you to calculate delta G using equilibrium constant. So if you rearrange this equation, you're going to get it in terms of K. So let me make sure I got this for you. And I don't want to make sure, I want to make sure you all get the right one. So you're probably going to have to use this equation. K is equal to E to the negative delta G naught over RT. So if you want, please take a picture of this because you're going to need this equation for your lab, for one question in your lab. And we'll talk about this on Wednesday as well, how equilibrium is related to spontaneity, delta G. All right, once you are done taking a photo of it, once you're done maybe even finishing up the question for their homework, you are free to go. If you have questions, I'll stay behind for another 5 to 10 minutes, okay? And I will upload the video and send you a link when I upload the video to my YouTube. I'll see you all Wednesday.
See you Wednesday, Dr. Z. Thank you.
Right, see you then.
Hi, Dr. Z.
Hey, Sean. See
Hey,
ya.
Dr.
Thank
Z, are
you.
we,
Bye.
for
See
the
ya.
quiz, are we just doing this stuff?
Yeah, for the quiz, you're gonna do pretty much this whole chapter, all the things we covered in this chapter.
Okay.
So 20 pages so far. Love it.
Okay, sounds good. See you Wednesday.
See you Wednesday.
Okay.
Dr. Z,
Yeah, Kim.
will you post chapter 16 annotated note on Canvas?
Yeah, once I put this up there on Canvas, I'll also give you the video, the YouTube videos as well. It might not be tonight though, it might be tomorrow. Or if it is tonight, it is really late tonight.
Okay.
Okay.
And also for the practice problem. So for practice problem number 5, did you put chapter 7 and chapter 16 together?